A computer simulation is a simulation, run on a single computer, or a network of computers, to reproduce behavior of a system. The simulation uses an abstract model to simulate the system. Computer simulations have become a useful part of mathematical modeling of many natural systems in physics, astrophysics, climatology, chemistry and biology, human systems in economics, psychology, social science, and engineering. Simulation of a system is represented as the running of the system's model. It can be used to explore and gain new insights into new technology and to estimate the performance of systems too complex for analytical solutions. Computer simulations vary from computer programs that run a few minutes to network-based groups of computers running for hours to ongoing simulations that run for days. The scale of events being simulated by computer simulations has far exceeded anything possible using traditional paper and pencil mathematical modeling. Over 10 years ago, a desert battle simulation of one force invading another involved the modeling of 66,239 tanks, trucks and other vehicles on simulated terrain around Kuwait. Using multiple supercomputers in the DOD high-performance computer modernization program. Other examples include a 1 billion atom model of material deformation, a 2.64 million atom model of the complex maker of protein in all organisms, a ribosome, in 2005, a complete simulation of the life cycle of Mycoplasma genitalium in 2012, and the Blue Brain project at EPFL, begun in May 2005 to create the first computer simulation of the entire human brain, right down to the molecular level. Because of the computational cost of simulation, computer experiments are used to perform inference such as uncertainty quantification. Simulation versus model. A computer model is the algorithms and equations used to capture the behavior of the system being modeled. By contrast, a computer simulation is the actual running of the program that contains these equations or algorithms. Simulation, therefore, is the process of running a model. Thus one would not build a simulation. Instead, one would build a model, and then either run the model, or equivalently, run a simulation. History. Computer simulation developed hand in hand with the rapid growth of the computer. Following its first large-scale deployment during the Manhattan Project in World War II to model the process of nuclear detonation. It was a simulation of 12 hard spheres using a Monte Carlo algorithm. Computer simulation is often used as an adjunct to, or substitute for, modeling systems for which simple closed-form analytic solutions are not possible. There are many types of computer simulations. Their common feature is the attempt to generate a sample of representative scenarios for a model, in which a complete enumeration of all possible states of the model would be prohibitive or impossible. Data preparation. The external data requirements of simulations and models vary widely. For some, the input might be just a few numbers, while others might require terabytes of information. Input sources also vary widely. Sensors and other physical devices connected to the model. Control surfaces used to direct the progress of the simulation in some way. Current or historical data entered by hand. Values extracted as a byproduct from other processes. Values output for the purpose by other simulations, models, or processes. Lastly, the time at which data is available varies. Invariant data is often built into the model code, either because the value is truly invariant or because the designers consider the value to be invariant for all cases of interest. Data can be entered into the simulation when it starts up, for example by reading one or more files, or by reading data from a preprocessor. Data can be provided during the simulation run, for example by a sensor network. Because of this variety, and because diverse simulation systems have many common elements, there are a large number of specialized simulation languages. The best known may be Simula. There are now many others. Systems that accept data from external sources must be very careful in knowing what they are receiving. While it is easy for computers to read in values from text or binary files, what is much harder is knowing what the accuracy of the values are. Often they are expressed as error bars, a minimum and maximum deviation from the value range within which the true value lie. Because digital computer mathematics is not perfect, rounding and truncation errors multiply this error. So it is useful to perform an error analysis to confirm that values output by the simulation will still be usefully accurate. Even small errors in the original data can accumulate into substantial error later in the simulation. While all computer analysis is subject to the GIGO restriction, this is especially true of digital simulation. Indeed, observation of this inherent, cumulative error in digital systems was the main catalyst for the development of chaos theory. Types. Computer models can be classified according to several independent pairs of attributes, including stochastic or deterministic. See external links below for examples of stochastic versus deterministic simulations. Steady state or dynamic, continuous or discrete. Dynamic system simulation, e.g., electric systems, hydraulic systems or multi-body mechanical systems, or dynamic simulation of field problems, e.g., CFD of FEM simulations. Local or distributed. Another way of categorizing models is to look at the underlying data structures. For time-stepped simulations, there are two main classes. Simulations which store their data in regular grids and require only next-neighbor access are called stencil codes. Many CFD applications belong to this category. If the underlying graph is not a regular grid, the model may belong to the mesh-free method class. Equations define the relationships between elements of the modeled system and attempt to find a state in which the system is in equilibrium. Such models are often used in simulating physical systems, as a simpler modeling case before dynamic simulation is attempted. Dynamic simulations model changes in a system in response to input signals. Stochastic models use random number generators to model chance or random events. A discrete event simulation manages events in time. Most computer, logic test and fault tree simulations are of this type. In this type of simulation, the simulator maintains a queue of events sorted by the simulated time they should occur. The simulator reads the queue and triggers new events as each event is processed. It is not important to execute the simulation in real time. It is often more important to be able to access the data produced by the simulation and to discover logic defects in the design or the sequence of events. A continuous dynamic simulation performs numerical solution of differential algebraic equations or differential equations. Periodically, the simulation program solves all the equations and uses the numbers to change the state and output of the simulation. Applications include flight simulators, construction and management simulation games, chemical process modeling, and simulations of electrical circuits. Originally, these kinds of simulations were actually implemented on analog computers, where the differential equations could be represented directly by various electrical components such as op-amps. By the late 1980s, however, most analog simulations were run on conventional digital computers that emulate the behavior of an analog computer. A special type of discrete simulation that does not rely on a model with an underlying equation, but can nonetheless be represented formally, is agent-based simulation. In agent-based simulation, the individual entities in the model are represented directly and possess an internal state and set of behaviors or rules that determine how the agent state is updated from one time step to the next. Distributed models run on a network of interconnected computers, possibly through the Internet. Simulations dispersed across multiple host computers like this are often referred to as distributed simulations. There are several standards for distributed simulation, including aggregate-level simulation protocol, distributed interactive simulation, the high-level architecture, and the test and training enabling architecture. Visualization. Formerly, the output data from a computer simulation was sometimes presented in a table or a matrix showing how data were affected by numerous changes in the simulation parameters. The use of the matrix format was related to traditional use of the matrix concept in mathematical models. However, psychologists and others noted that humans could quickly perceive trends by looking at graphs or even moving images or motion pictures generated from the data, as displayed by computer-generated imagery animation. Although observers could not necessarily read out numbers or spout math formulas, from observing a moving weather chart they might be able to predict events much faster than by scanning tables of rain-cloud coordinates. Such intense graphical displays, which transcended the world of numbers and formulae, sometimes also led to output that lacked a coordinate grid or omitted timestamps, as if straying too far from numeric data displays. Today, weather forecasting models tend to balance the view of moving rain, snow clouds against a map that uses numeric coordinates and numeric timestamps of events. Similarly, CGI computer simulations of CAT scans can simulate how a tumor might shrink or change during an extended period of medical treatment, presenting the passage of time as a spinning view of the visible human head, as the tumor changes. Other applications of CGI computer simulations are being developed to graphically display large amounts of data in motion, as changes occur during a simulation run. Computer simulation in science. Generic examples of types of computer simulations in science, which are derived from an underlying mathematical description. A numerical simulation of differential equations that cannot be solved analytically. Theories that involve continuous systems such as phenomena in physical cosmology, fluid dynamics, continuum mechanics and chemical kinetics fall into this category. A stochastic simulation, typically used for discrete systems where her events occur probabilistically and which cannot be described directly with differential equations. Phenomena in this category include genetic drift, biochemical or gene regulatory networks with small numbers of molecules. Specific examples of computer simulations follow. Statistical simulations based upon an agglomeration of a large number of input profiles, such as the forecasting of equilibrium temperature of receiving waters, allowing the gamut of meteorological data to be input for a specific locale. This technique was developed for thermal pollution forecasting. Agent-based simulation has been used effectively in ecology, where it is often called individual-based modeling, and is used in situations for which individual variability in the agents cannot be neglected, such as population dynamics of salmon and trout. Time-step dynamic model. In hydrology there are several such hydrology transport models such as the SWMM and DSSAM models developed by the U.S. Environmental Protection Agency for river water quality forecasting. Computer simulations have also been used to formally model theories of human cognition and performance, e.g., ACT-R. Computer simulation using molecular modeling for drug discovery. Computer simulation for studying the selective sensitivity of bonds by mechanochemistry during grinding of organic molecules. Computational fluid dynamics simulations are used to simulate the behavior of flowing air, water and other fluids. 1, 2 and 3-dimensional models are used. A one-dimensional model might simulate the effects of water hammer in a pipe. A two-dimensional model might be used to simulate the drag forces on the cross-section of an aeroplane wing. A three-dimensional simulation might estimate the heating and cooling requirements of a large building. An understanding of statistical thermodynamic molecular theory is fundamental to the appreciation of molecular solutions. Development of the potential distribution theorem allows this complex subject to be simplified to down-to-earth presentations of molecular theory. Notable, and sometimes controversial, computer simulations used in science include Don Meadows' World 3 used in the Limits to Growth, James Lovelock's Daisy World and Thomas Ray's Tierra. Simulation environments for physics and engineering. Graphical environments to design simulations have been developed. Special care was taken to handle events. The open project Open Source Physics was started to develop reusable libraries for simulations in Java, together with easy Java simulations. A complete graphical environment that generates code based on these libraries. Computer simulation in practical contexts. Computer simulations are used in a wide variety of practical contexts, such as analysis of air pollutant dispersion using atmospheric dispersion modeling, design of complex systems such as aircraft and also logistics systems, design of noise barriers to affect roadway noise mitigation, modeling of application performance, flight simulators to train pilots, weather forecasting, forecasting of risk, simulation of other computers as emulation, forecasting of prices on financial markets, behavior of structures under stress and other conditions, design of industrial processes, such as chemical processing plants, strategic management and organizational studies, reservoir simulation for the petroleum engineering to model the subsurface reservoir, process engineering simulation tools, robot simulators for the design of robots and robot control algorithms, urban simulation models that simulate dynamic patterns of urban development and responses to urban land use and transportation policies. See a more detailed article on urban environment simulation. Traffic engineering to plan or redesign parts of the street network from single junctions over cities to a national highway network to transportation. System planning, design and operations. See a more detailed article on simulation in transportation. Modeling car crashes to test safety mechanisms in new vehicle models. Crop soil systems in agriculture via dedicated software frameworks. The reliability and the trust people put in computer simulations depends on the validity of the simulation model. Therefore, verification and validation are of crucial importance in the development of computer simulations. Another important aspect of computer simulations is that of reproducibility of the results, meaning that a simulation model should not provide a different answer for each execution. Although this might seem obvious, this is a special point of attention in stochastic simulations, where random numbers should actually be semi-random numbers. An exception to reproducibility are human-in-the-loop simulations such as flight simulations and computer games. Here a human is part of the simulation and thus influences the outcome in a way that is hard, if not impossible, to reproduce exactly. Vehicle manufacturers make use of computer simulation to test safety features in new designs. By building a copy of the car in a physics simulation environment, they can save the hundreds of thousands of dollars that would otherwise be required to build and test a unique prototype. Engineers can step through the simulation milliseconds at a time to determine the exact stresses being put upon each section of the prototype. Computer graphics can be used to display the results of a computer simulation. Animations can be used to experience a simulation in real time, e.g., in training simulations. In some cases, animations may also be useful in faster than real-time or even slower than real-time modes. For example, faster than real-time animations can be useful in visualizing the build-up of cues in the simulation of humans evacuating a building. Furthermore, simulation results are often aggregated into static images using various ways of scientific visualization. In debugging, simulating a program execution under test can detect far more errors than the hardware itself can detect at the same time. Log useful debugging information such as instruction trace, memory alterations and instruction counts. This technique can also detect buffer overflow and similar, hard-to-detect errors as well as produce performance information and tuning data.